Okay, let's talk about sulfur nucleophiles in relation to nucleophilic additions to aldehydes and ketones. All right, so as you will probably expect, the mechanism is going to be very much identical to what we saw in the situation with alcohols, because thiols, after all, are nothing more than the sulfur derivatives of alcohols. So you could do this with simple, thiol molecules. You could also do it with dithiols, as shown right here. And I'm going to show you the acetal formation in particular, right? So just like we saw in the previous video, you add a little bit of acid catalyst to your reaction mixture. You carry this in ideally dithiol solvent, or at the very least, you use an organic solvent that is not nucleophilic with a high enough concentration of your dithiol to carry out this reaction. Now, one thing I should probably warn you is that if you do try to do this, and I don't recommend you to do this on your own, much less in your house, these molecules are notorious for having very, very unpleasant odors. they're not, they're very smelly. They're very smelly. And basically, when people say this smells like crap, that smells like crap, this is crap, they're probably talking about a sulfur compound, just so you know. So anyway, oh, and case in point, gas, natural gas that either you have at home or that you use in the laboratory, natural gas doesn't have a smell, but you can always spike it with a sulfur component. Usually it's dihydrogen sulfide, and you don't need much of it. You know, we our sensory cells in our in our noses are actually pretty good at detecting sulfur, and so we don't need much of a concentration. So we spike natural gas with it to actually know that we have a leak at home or somewhere else. All right, but anyway, let's get on with this reaction. So we protonate ultimately the carbonyl with the actual catalyst, the acid catalyst, and when they're forming the protonated carbonyl, we have our neutral dithiol present in here. And the dithiol is actually a much better nucleophile than the oxygen counterpart. So this reaction goes pretty smoothly. The sulfur attacks the carbonyl carbon. The set of pi electrons goes back to the oxonium oxygen, now making that oxygen neutral, but now the sulfur is got a positive charge because it's got 3 bonds. Then the proton of that sulfur gets removed, probably by the second sulfur present in that same molecule, just like we saw with the diol molecule. So this attacks the proton, the electrons go back to the sulfur, and the molecule basically just rearranges itself and reshuffles the proton, because now that proton is going to be given to the hydroxyl unit, right? So in other words, the oxygen atom attacks that proton, the electrons go back to the sulfur, and you generate a good Levin group, aka water. So your sulfur atom donates its electrons to create a carbon-sulfur double bond. At the same time, you do kick out that water molecule. And just like we saw before, this carbonyl, which is part of a sulfonium cation, is very electrophilic. So the sulfur, being a great nucleophile, attacks that carbon, kicking away the electrons back to the sulfonium cation, and producing a 5-member ring. And just like I told you before, you got to count your atoms, right? So you're attacking the carbonyl, and you're going to go around, and that has 1, 2, 3, 4, 5 second row elements, so you form a 5-member ring. And then, of course, the last event is that you remove that proton with a base. Probably the dithiol will do the trick. If you end up using water to show this, technically, okay, that could happen as well, because you are producing a little bit of water in the reaction. All right, so some kind of base comes and removes that proton, attacks the proton, the electrons go back to the sulfur, and that produces your neutral dithiol acetal derivative. Okay, so you might say, all right, well, fantastic, same stuff as the oxygen stuff. Okay, so so what? All right. Well, there's a couple things that need to be mentioned. The first thing is that sulfur, being a better nucleophile than oxygen, makes this reaction rather smooth. The fact that we're using a dithiol means that we go pretty much guaranteed to the acetal stage, especially under acidic conditions. But the second thing about it is that there's one additional reaction that we can employ and take advantage of, because unlike oxygen, sulfur has a much easier time changing oxidation states. And in this case, we can easily reduce sulfur by using something called as Raney Nickel. And specifically, the reduction is going to be such that for every carbon sulfur connection you have, you're now going to create a carbon hydrogen connection. So in essence, this is a means by which we can take a carbonyl and turn it back into an alkyl or alkane molecule. So Raney Nickel is basically named after the scientist that came up with the actual combination, the actual chemical itself. Yeah, and he came with this particular material back, I want to say the 50s, maybe 60s, while he worked at one of the chemical companies at the time. And basically, what it is a combination of nickel with aluminum, which is got plenty of electrons to be donated, right? These two things really want to oxidize and donate electrons. So the nickel aluminum combination is what is known as Raney nickel, and it is rather, pyrophoric. So you kind of have to be careful with that stuff. But here is, showing you like another batch of the nickel aluminum. Depending how fresh it is, and what the proportions are, the colors can be a little bit different. But you can kind of see the porous, nature of the material. So ultimately, yes, the sulfur molecules do attack these metals, and then the metals provide the electrons to give way to the reduction ultimately. So I'm going to try to show you how that happens. Now, obviously, hydrogen has to be involved if you're going to end up with an alkane or an alkyl, and Raney nickel does not contain that. So what you have to do is literally pump in some hydrogen gas into the mixture. So Murray Raney, right, he basically investigated this type of approach. And as I mentioned to you, the carbon here on the very right is now going to be fully hydrogenated, right? It did have a hydrogen to begin with, and then we're going to substitute those two carbon sulfur connections with hydrogen. So the way that this ultimately happens is that, yes, the sulfur completely gets it gets reduced to full completion. It basically goes all the way to the sulfide. And because the nickel is providing the electrons for this reaction to happen, the nickel becomes positively charged. So you kick out and produce nickel sulfide in the process. Also, you break the connections to the carbon sulfur on the back end, which means that you produce some ethylene in the process. And that's basically a gas. So these are simple things to separate away from your organics. So in essence, this is a very, elegant and very efficient reaction. So keep this in mind, because in some situations when you're doing synthesis, maybe you're trying to elongate the carbon chain or something to it, but going from alkane to alkane is not a trivial thing. However, you can always go from an alcohol to a ketone or an alcohol to an aldehyde. Then you can do any type of reaction you want to, a nucleophilic reaction to it, like extend the carbon chain, reform the carbonyl bond, and ultimately you can remove that CO double bond by doing this Raney nickel reduction. So it actually kind of helps out to kind of go from one type of alkane to another, if that's kind of the thing you're trying to do. So, in summary, basically this is the idea, right? If you have that carbonyl, you could react it with the dithiol molecule, followed by hydrogen in the presence of Raney nickel, and you got yourself your corresponding alkane. All right, so to kind of complete the picture, of course, this is what I mentioned to you already a few seconds ago. You can make the carbonyl from the alcohol, right? And then you have the whole sequence of events, right? Carbonyl can go back to the alcohol. You can make modifications there, or you could turn that alcohol back into the carbonyl and then turn it into an alkane. So you have routes of attack that you should consider based on this. So on the next video, we're now going to look at nitrogen nucleophiles, and we'll see what other characteristics, chemically speaking, they present. So I'll catch you in the next video.